And so let's say we have a number of bytes. I'll just show these as a group of squares up here. And that's going to be the table of contents or the root directory. So these have different names, directory or folder or table of contents. These have all been used in computer science. We still use directory and folder interchangeably. So the root directory would just be a series of bytes that has names of the files or the chapters and then pointers to where they start. And then we'll take a look at some blocks of files and chapters. I'm just going to show a few squares here. It's going to be rather simplified, but we'll show you what the problem can be. So there's some empty sectors. Let's say they're like the pages on a book that hold, well, on modern disks, a sector would be 512 bytes. Some disks it might have been 128 or 256, but we'll just know that that's a block of so many bytes to where we can hold information. So here's a block that can hold so much 512 bytes, another block can hold 512 bytes, etc., etc. Now what we're going to do is start writing files on here, or chapters, or whatever you want to call them. So I'm going to use green to represent the first one. I'm going to put the name in the root directory and a pointer to the first sector. And so I'll just put that there. There's the first sector, but it's going to take more than one sector. Let's say it takes 3 sectors. So there's that first file. So we have a pointer to it. It's 3 sectors long. There might be some housekeeping information to tell how long that is so we don't have to search it. And there's our first file or chapter in this disk. Then our next one will have a name in the root directory. And of course this root directory is tacked on the end there, but I'm just moving it up here. There's the name and pointer to the next one. Let's make that 2 sectors long. And let's make another file over here. Third file, there's the name in the directory with a pointer, and it's going to be, let's make that 4 sectors long because we can. And I'm going to get one more color here just to make one more file, just to complicate things a little bit. I don't know if you can see that purple on the video or not, but there we have it. There's another file, and let's just make that 2 sectors long. Okay, now let's say we decide to erase file number 2. So what we're going to do is we don't actually erase them. We put a mark in the directory that says this is an erased file, but we'll just erase it like this. And of course these bytes are not erased, they're just marked as usable. We'll tell how that's done in a moment. But we'll just erase them to show that those are no longer part of a file. So the system sees there's an empty spot in the directory up here and says, I'll put my name right there. And then it goes to put the data on the disk, and let's say this particular file is 4 sectors long, so it goes, okay, I'll put it there, and there's a problem. So how are we going to solve that problem? Well, we could solve it by saying, well, I just can't use those sectors anymore, unless I find a file that's 2 bytes long, so I would just have to not use those 2 sectors, and I could put the files right here. And now I come up with another file. Let's say this has been done a number of times, so I have some empty spaces with different lengths of sectors. It could get very difficult to find a space to put files if I end up with 2 sectors here, 1 sector there, 3 sectors there. That could be quite complicated. So it's not really a practical application to try to just fit the files contiguously like that. But let's have a system where we don't need to be contiguous. Let's have a file allocation table. So now we have some more sectors somewhere else. I'll put, just because that's where it is in the real world, let's put it before the directory. So here are some bytes that make up the file allocation table. So that's the file allocation table. This is the directory, or the root directory. The root directory. There can be other directories. All a directory is just a file that's organized with names and pointers. So we can have subdirectories and directories in directories. In a way, it's just a bunch of pointers, really. But there's our file allocation table. And our file allocation table is going to tell us which sectors are used. In fact, this file allocation table needs to be as long as that. We need to have an entry for every single sector on the disk. So let's draw that out here. may not be perfect, but it'll do. Now, each one of these is just a few bytes. It's not a whole sector. So this is like 512 bytes. This is going to be, depending on how big the disk is, 2, 4, 6, or just a few bytes. So it doesn't take that much room for the file allocation table. Now this is an obsolete way of doing things, but it was the way it was done for quite some time, and on some disks it's still done. If you happen to have a floppy disk, whatever that is, you still have file allocation tables. But anyway, here's how it works. So the first file is going to simply say, okay, if there's an entry here, it means that sector is in use. And that entry is going to point to the next sector in the file. So let's say, if I try to draw the numbers, it'll get confusing. It's just going to have a number that points to the next one to say my next page is the very next page. So here's page 0. Here's entry 0 represents page 0. Entry 1 represents page 1. Entry 2 represents page 2. And what this simply says is, okay, there's a number here, which means that page 1 is used, and the number points to the next sector that holds the next page. So it says the next one's there. And there's 3, so this one's going to point to the next one. And this will have a marker that says that's the end of the file. So I'll just put an X there saying that looks like the data. Let's just put a EOF, a code that says this is the last sector in the file. So the system has to go in and say, okay, here's my file name in the directory. It starts here. I'll go grab my information. Now I have to go to the file allocation table and see which one is the next sector. Okay, it's the next one. So I go here and get that. Then I have to go up to the file allocation table and see what the next sector is. Okay, it's that one. I go get the data, and oh, that's the end, so I'm done. Now let's go take a look at what happened with our orange file here, because we need that. It's going to be 4 sectors long. So the first 2 sectors are there, then we skip way over to here, and now we have to be able to get that data. So let's go back and look at how we get that. So the system goes to the directory, gets the name and gets the pointer to the first sector, goes and grabs that data. Then it goes, let's see, this is sector 0, 1, 2, 3, sector 3. So it goes to the file allocation table for sector 3, and that has a pointer to the next sector, points to sector 4. So it goes down here, grabs sector 4, goes and puts it wherever it's going to put it. Then it goes back to the file allocation table, which has a pointer that goes all the way to, what's that, 4, 5, 6, 7, 8, 9, 10, 11, 12. Points all the way over here. So the number here is going to be the number 12, saying next sector is sector 12. So, oh, okay, I go to 12, grab that one, and then that one points to the next sector, which is going to be end of file. And so the system says, okay, let's see, that one says to go to the next sector, so I'll grab that, then go to the next one. Okay, end of file, I'm done. So this file allocation table, think of it like a book. Now, this is going to take a little different method of reading. I go and I find a chapter. Okay, how about chapter 2? Page 9. Let's see, where's page 9? Okay, chapter 2 starts here. I go and read the page, and we intuitively know, well, you just go to the next page. But this might be like that. This is what we call a fragmented file. Well, this book might be fragmented, so when I finish the page, I can't simply go to the next page. I now have to go back to the front of the book, to an imaginary page allocation table. Okay, I've read page 2. What's the next page? Oh, it's page 3. Now I can just flip the page. Oh, okay, I can read page 3. Okay, I'm done. I can't just go to page 4. It might not be the same chapter because of the way we've just moved things around. Of course, we wouldn't do this with a book, but it's, as I've shown, it's the practical way to do it in memory or with a computer. So I finish page 10 here. I said page 3, but I finish page 10, and I go to the end, and I have to go to the page allocation table. Okay, after reading page 10, go to page 14. Oh, okay, there we go, page 14. And so I have to read a page, go to the allocation table, find out what the next page is, read that page, go to the allocation table, find out what the next page is, read that page, and that's the way things might be organized on a disk, because when we first write them down, everything's contiguous, nice and easy like a book. But as we erase things and put new things in and find that we have to, it's just not practical to move all the stuff. how much time would that take, especially with a big disk? So instead of moving things, we simply let things get fragmented. And that's kind of a silly, cumbersome way for us to do it, but it's no problem for computers. They can do it very quickly. There are issues, but we'll talk about that in a moment. So think of it like that. It's a data structure we use in computers. Now, if you've been studying data structures, you've probably never heard of this, but this is a way that we do structured data in computers, and hopefully this is helpful to get us ready to study data structures. So that's the file allocation table system. Now, the problem with that is that things do get fragmented, and that can increase the seek time to find a file because the disk is spinning. We go in, we grab a couple of sectors, and then, oh, the next sector's on the next track. We have to move the head to the next track. Oh, it's already passed. We have to wait for it to come around again and get the next couple of sectors. And then, oh, well, we have to move track again, wait for it to come around, get the next one. So that can be a mess. So we used to have these programs called defragmenters. I haven't used anything like that in a while because modern operating systems are designed to avoid fragmentation. You may have to defragment things sometimes, especially a disk that's been around a while, but they're a little smarter in how they allocate things. Instead of putting things in sequence, they'll put one file here, and then they'll put the next file, somewhere in the middle, and then split the difference and try to keep things from getting fragmented. But the defragmenter would go in there and move everything around, literally move all the data around so that they're all contiguous, and so these would all be together, and we could just read them right off the disk. So that's one problem with the file allocation table. The other problem is that the disk read head has to go back and forth, back and forth, back and forth, back and forth to read the file allocation table and to read data. So it's, they read that, read that, read that, read it, just like doing the book. Had to read the page, go back, find the cable, go back, read, pretty much a mess, slowed things down. So we have better ways of doing that today. I'm not going to talk about that because this is not a class in disk structure, but a class in data structures. I just wanted to show that as the logical next step from the simple book that we have on a CD-ROM, where we have just a table of contents and contiguous files. The next step is this. Okay, so there is some ideas of what data structure is, why we have them, and some actual implementations. I'm not showing you the exact numbers and stuff here. That might be more confusing than useful, but you could extrapolate to this to know, well, that's just a number. That would be the number. This is entry 0, and the number would be 1, meaning the next one is 1. And this one would have the number 2, saying the next one's 2. This would have the number, 0, 1, 2, 3. That would have the number 4, saying the next one's 4. And then it says the next one's 12, so the number here would be 12, saying go to 12. The number here would be 13, saying go to 13. So it's just a series of numbers there, and if you ever have to dig your way through a disk like I had to one time, how do you think I know about this? I had to dig through a disk to manually recover some mangled files. So I learned fairly intimately how these systems work. If you ever have to do that, well, you see an idea of how that works. And so I think I've given you enough information to know how this is actually implemented. So that is a book or a CDFS system, and this would be the FAT file system that was ubiquitous for quite some time in PCs. So that is an introduction to data structures, telling us why we need data structures and how some of them are put together. Some examples of how something familiar like a book can be extrapolated to create a data structure that's used in computers. And so now we've taken a look at that, and in the next video we'll start taking a look at some data structures you may actually learn about if you study data structures, and some real-world examples and how they are implemented. So if you think this video is useful and informative, please give me that thumbs up down below. It really helps the channel. Don't forget to subscribe. Hit that gray bell when you do so you get notified when I put up new videos. And as always, a big thank you to my patrons and members and other donors. You are making this possible, and thanks to everyone for watching.